Solutions about singular points. If we talk about the word singular, it's always in comparison to its opposite. And the opposite here of singular would be ordinary. Singular has the understanding, whether it's linear algebra or here or any concept in mathematics, singular has the connotation that something does not exist at that particular point. There's either no solution. In linear algebra, we say that a matrix is singular if it has no inverse. And so here, we can talk about solutions about a point, say, for example, that's ordinary, or we can talk about the solutions about points that are singular. They use the phrase about because, by all means, at that point, there is no solution. So, but in that neighborhood, you could find a relatively small or whatever size neighborhood by which you may have some solutions containing there. So we can get close as possible to those values, those points where we have some discontinuity, and you can examine the so-called solution. So we begin by first talking about the definition of a singular point, and we can go into depth to talk about if it's singular, it could be regular or it could be irregular. And it's going to be regular based on the idea that if you can do some factoring, and you remember in calculus where you had certain functions and they would ask you, is this function differentiable or is it continuous? And then it would talk about, can you remove some discontinuities from that particular function, basically by factoring out, certain terms from the numerator and denominator. And it seems like that factor is no longer there after you factored it out. So you call that a removable discontinuity. It's still said to be discontinuous at that point, but in some analytical sense, you did some algebra, you removed it. So here, if we have a singular point or a point of discontinuity, can you do some factoring to somehow remove that term? The emphasis on the removal is about p of x, y double prime plus p of x, y prime plus qx times y equal to 0. So we examine that if we have a term up top, a sub 2 of x times y double prime, if you divide a sub 2 of x into the entire second order differential equation, what happens to the denominator of p of x? What happens to the denominator of q of x? So we examine that. I have a little small note here to explain it, and then from there we'll work some problems where they first ask, instead of trying to solve by power series, determine whether or not certain points for the differential equation are regular, singular, or irregular, singular, or if they're ordinary. And so the definition here that's given by the author, the definition is somewhat misleading to try to actually understand what it means. We'll look at a problem and I'll show you. But here, the definition for a regular or irregular singular point. A singular point x equal to x naught is said to be regular, singular, for the differential equation number 1 up there. That's basically just the second order linear differential equation. If the functions p of x equal to x minus x naught, a linear factor, times p of x, and q of x equal to x minus x naught to be squared times q of x, capital Q of x, or both analytic at x naught. Analytic is just a fancy word of saying that something can be calculated there or reduced to be able to solve by a power series. The definition of analytic at x equal to x naught basically means that you can find a power series at x equal to x naught. Well, that's our whole goal, is to be able to find a power series with these particular differential equations. So if x naught is a singular point, you must determine whether or not x naught is regular or it's an irregular singular point. Here's the note here that I think is important. I think this note here somewhat sums up everything in terms of what we are talking about. If you have a singular point, and we'll look at in just a moment, taking the coefficient of y double prime, looking at that coefficient, determining whether or not the terms or the factors are singular or ordinary. And if it's singular, then you want to be able to answer the question, is it regular singular or is it irregular singular? So if x minus x naught appears with the first power, it says here at most the first power in the denominator of p of x, and it appears at most 2 or to the second power in the denominator of q of x, excuse me, then x equal x naught is said to be a regular singular point. Otherwise, if that doesn't happen, it's going to be irregular singular. Just a couple of examples here. So classification of singular points. We're looking at this differential equation here. And this blue is fine. You first look at the coefficient for y double prime. So the coefficient there is this x squared minus 4. It's all to be squared. We set that equal to 0. Well, that implies that x is equal to plus or minus 2. Plus or minus 2 for this differential equation are said to be the so-called singular points. How do you find the singular points or the ordinary points? You take the coefficient of y double prime, set it equal to 0. Whichever values give you 0, those values are called singular points. All other points are called ordinary. Okay. All other points on the real number line are called ordinary. But then for the question of singular, they want you to classify whether or not it's regular singular or it's irregular singular. So what we do is you just take the factor or the coefficient for y double prime and just divide it through each of the terms there in that differential equation. And then you're going to examine the denominator for y prime and then examine the denominator for y. And we'll look at the schematic scheme. Well, here, p of x is the factor associated with y prime. You remember the form looks like y double prime plus p of x times y prime plus q of x times y is equal to 0. So what this note here that I have the star by, what it says is that if you take a factor x minus x naught, look at x minus 2, if the power of its exponent for p of x occurs at most 1, and then its power for q of x occurs at most 2, I didn't mean to white it out. Then we say that that particular value, x equal to 2, is said to be regular singular. So x equal to 2 is a regular singular point. Now, if that doesn't happen for a factor, two things you're looking at. Look at your denominator for p of x. If the power is at most 1 for p of x, and if its power is at most 2 for q of x, it's regular singular. Otherwise, if any of that fails, it's irregular. So you come here to the factor x equal to -2, which is this term here, that guy right there. You look at its power here for p of x is at most 2. It's supposed to be at most 1 for regular. So you stop there and say this guy is irregular singular. So x equal to -2 is irregular singular. Now, why do they make the distinction? Well, here's the reason. We can solve a differential equation by power series if we know that the center that we're examining, that it is, and we're kind of looking around at the neighborhood of it, but if that point that we're examining is regular singular, then we have a theorem that says I'm supposed to find, hopefully, 2 solutions. Okay? We have a theorem that says we can do that. If the point that we're examining is irregular singular, then we don't know what to do. Okay? Obviously, the problems that we have for you to solve the differential equation using the power series method in this section, those problems, we will be asking you to find the solution about a regular singular point. It's already understood to be so. All right. So now, in problems 1 to 10, determine the singular points of the given differential equation. Classify each singular point as regular or irregular. So if you take number 1, if we start with that one, we're going to divide everything through by x to the third. So we have y double prime plus 4 over x times y prime plus 3 over x to the third times y is equal to 0. All right. So this is p of x, and over here, this is q of x. So notice that the term here, the linear factor x minus 0, it occurs to the first power for p of x, which that's what it's supposed to do. But for q of x, it's supposed to occur, the power that is supposed to occur at most 2. Here, the power is 3. So that means that x at x equal to 0, which is the x naught, the term. Here, this guy is irregular singular. What about number 3? So if we divide, oh, by the way, number 1, you take x cubed equal to 0, so that implies that x is equal to 0. So look at number 3. We have that term x squared minus 9 to be squared. We set that equal to 0. And so here, this implies that we have x is equal to plus or minus 3. So we know off the bat that plus or minus 3 singular points, but we don't know right now if they're regular or if they're irregular. So we have to find that. So we divide in number 3, we divide the x squared minus 9 to be squared throughout the entire differential equation. So that leaves us with y double prime plus 1 over, I guess I better write everything out. So this is x plus 3. That's all over. Now this is x minus 3 to be squared times x plus 3 to be squared. This is times y prime plus 2 all over x minus 3 to be squared times x plus 3 to be squared times y. That's equal to 0. Well, we're going to do some factoring and some cancellation for p of x. So one of these x plus 3's will cancel out with one of those terms there. We just have left an x plus 3. And so this is number 3 again. So this is y double prime plus 1 all over x minus 3 to be squared times x plus 3 times y prime plus 2 all over x minus 3 to be squared x plus 3 to be squared times y is equal to 0. So if you look at the x plus 3, this guy gives us x equal to negative 3. Then if you look at the x minus 3, that gives us x equal to 3. So let's take the x equal to negative 3, or the x plus 3 factor. Its power here for p of x is 1, and its power for q of x is 2. So that means that it's regular singular. So for number 3, x equal to negative 3 is regular singular. Well, what about x equal to 3? Well, that's the factor x minus 3 to be squared here for p of x, and then over for q of x is x minus 3 to be squared as well. Its power is supposed to be, for regular singular, the power for p of x is supposed to be at most 1. At most 1 means it could be nothing, that is 0 power 1, that kind of thing. Here it's 2, so you stop there and say it's irregular singular. What if the root or the term is imaginary? Well, you just still apply the same concept. Number 8. So for number 8, you have x equal to 0 and x equals to plus or minus I. These are your singular points. All other points, obviously, if you can identify the singular, all other points are ordinary. It would take courses like either functional analysis or Fourier analysis to look at solutions about imaginary terms and look at solutions about the so-called irregular singular points. They tend to go a little bit further, but it's not necessary here because when you're dealing with real terms, you're either dealing with solutions about an ordinary point or solutions about a regular singular point for ordinary terms that exist in space, in nature. So we take number 8, we're going to divide through by a of x, and so we end up with y double prime plus 1 all over, this is x, break this down, this is x minus I to be squared, this is x plus I to be squared times y is equal to 0. Right. So we're examining at x equal to 0, at x equal to I, and x equals to negative I. Well, we know they're all singular because they were from that a of x, that a sub 2 of x, that first term multiplied times y double prime. We set that coefficient equal to 0, and so we got x equal to 0, we got x equal to plus or minus I. So my question to you is, x equal to 0, is it regular or singular? X equal to I, is it regular or singular? Is it regular or irregular, excuse me, and then x equal to negative I, is it regular or irregular? Okay, you see, all of them? Yeah, they're all irregular, right? So the question is, you don't see the term p of x, right? So you say, I don't see p of x. But it says that the power in its denominator has to be at most 1. I told you at most 1 could be none, right? 0 or 1. So that's classified here. So then the power for q of x, which is what I have here, the term multiplied times y, the power downstairs can be at most 2. That means it can be none, 1, or 2. Right? So all these guys are the same. They are regular, singular. So if they're regular singular, then we're able to state a theorem, and the theorem helps us at getting at the solution for a power series. This is Frobenius' theorem. This theorem says that if I know that I'm calculating the differential equation about trying to solve for a power series, and I know that the term that I'm trying to calculate the solution, the interval, this so-called interval, 0 less than x minus x naught less than r, if I know that x naught is a regular singular point, then I'm able to get a solution. He says here that there exists at least one solution. That means that you're guaranteed to have one, possibly 2, but definitely at least 1. He introduces a different term here. He introduces this n plus r, but it's that r factor. That is the x minus x naught raised to the r power. And then he combines that within the summation, since x minus x naught to the n has the same base, so we get in the summation x minus x naught raised to the power of n plus r. Well, that r is the challenge for us. Once we can somewhat deal with that, then the problem works out the same way that it worked in the previous two sections. Okay. Now my instructions to this are the same instructions, but I had to add in here how to deal with this R index. He calls them indices or indexes. So steps here to solving a differential equation using power series. with solutions about singular points, and particularly it's regular singular. So you're gonna have an x to the r term showing up in those summations. Let's see if we can factor that guy out. The better for us. So you're gonna factor it out. Replace n with some k factor, the same instruction from before. Evaluate each summation so that each summation starts at the same value, the same information as before. Here, something different, because I have this r term. Determine the values of r from step number 3. Hopefully that should be evident. R is called an index. We call the values of R the indicial roots. Those roots for R will somewhat guide the solution. And whatever the solution is going to be is first going to be controlled by this R term. So now after you do that, you should be able to factor out, 2 steps number 4. How did that happen? Not good. Factor out x to the k, and then write the summations as one summation. Again, that's something that we did before. And the rest of the steps somewhat follow the same, but again, in particularly as it relates to this factor or this indicial root of R. So you want to find a formula for the C sub k, determine the pattern for each indicial root, and I'll show you that. We'll work a problem here. And then write the 2 solutions if possible, if it's 2. It should be at least 1 with respect to those indicial roots R. And so let me show you that, and we'll just take our time trying to work through this problem because it's somewhat long, and the problem on the test that I give you won't be as long as this one, but all the steps will be applicable. In problems 15 to 24, x equal to 0 is a regular singular point. Well, let's take number 19, for example. Set 3x equal to 0. That implies that x is equal to 0. So we know that it's singular. Right? And then, if you divide 3x throughout the entire differential equation, then we have, see, this implies this is y double prime plus 2 minus x all over 3x times y prime minus 1 over 3x times y equal to 0. And you can see here that 3x, where x here is raised to the first power for p of x, and then is raised to the first power for the q of x, and that meets the criteria for a regular singular point. So indeed, x equal to 0 is a regular singular point. Here, show that the indicial roots of the singularity do not differ by an integer, whatever that means. Who cares, right? We're just going to solve the dang on problem. So use the method of Frobenius to obtain 2 linearly independent solutions, power series solutions about x equal to 0. Now, what is that theorem again? Well, that theorem says this, that if you know that x equal x naught is a regular singular point, then you can write the value y in a power series of this form. So here for our problems, our x naught is 0, so y looks like the summation as n goes from 0 to infinity of c sub n times this x to the n plus r. So let's see. Let's take number 19. So we say by Frobenius, y is equal to the summation as n goes from 0 to infinity, c sub n times x to the n plus r. This problem has the second derivative, so we find y prime and we find y double prime. So y prime is the summation as n goes from 0 to infinity, c sub n times n plus r raised to the n plus r minus 1. And y double prime is equal to the summation as n goes from 0 to infinity of c sub n times n plus r minus 1. Well, it's n plus r, and then times n plus r minus 1. Times x to the n plus r minus 2. So for the problem, we're going to replace the y double prime with the power series that we have here, replace the y prime with this associated power series, and then replace the y with the power series that's there that we're assuming. So this is 3x y double prime. I'll write it like this. This is plus 2y prime. I better break up that term there, minus x times y prime minus y is equal to 0. Look, for those students who came in after the advisor from UAH was here, he came and spoke to the class the first couple of minutes. If anyone is interested in going to UAH, you've signed up, you have some questions about that. He's a advisor for their engineering department. He'll be out here in the lobby after class. He said he'll be there, I think, till about 1 o'clock today. So if you want to go out and talk with him, he may have some information that he can give you as well about UAH. Okay. So here, so we have 3x times the summation as n goes from 0 to infinity, c sub n times n plus r times n plus r minus 1 times x to the n plus r minus 2. And this is plus 2 times the summation as n goes from 0 to infinity. This is y prime, so this is c sub n times n plus r times x to the n plus r minus 1. And now this is minus x times y prime, so minus x times the summation as n goes from 0 to infinity, c sub n times n plus r times x to the n plus r minus 1. And then this is minus y, so that's the summation as n goes from 0 to infinity of c sub n times x to the n plus r, and that's all equal to 0. All right. So let's do this. There's an x term that's sitting out here with that 3x, and then for this term here minus x, that x is sitting there. It needs to go inside because it's too cold outside for them. Okay, so we're gonna bring them inside the house. So we write this as 3 times the summation as n goes from 0 to infinity, c sub n times n plus r times n plus r minus 1 raised to the n plus r minus 1 plus 2 times the summation as n goes from 0 to infinity, c sub n times n plus r times x to the n plus r minus 1 minus the summation as n goes from 0 to infinity, c sub n times x to the times x c sub n times n plus r, times x to the n plus r. You put that x to the first power times x to the negative 1, so we just get x to the 0 there. And then we have that last term minus the summation as n goes from 0 to infinity of c sub n times x to the n plus r is equal to 0. Now the first thing we're going to do is we're going to factor out, yes sir? Yes sir? I just forgot to put the x there. It's x raised to that power. Okay. Yeah, thank you. So, first step, we're going to factor out x to the r. So we have x to the r taken out from everywhere. So it has left brackets 3 times the summation as n goes from 0 to infinity, c sub n times n plus r times n plus r minus 1 times x to the n minus 1 plus 2 times the summation as n goes from 0 to infinity, c sub n times n plus r times x to the n minus 1 minus the summation as n goes from 0 to infinity, c sub n times n plus r times x to the n minus the summation as n goes from 0 to infinity, c sub n times x to the n, close that up, set that equal to 0. Now you can factor out x to the r out because the summations, they run with respect to n. The summation as n goes from 0 to infinity. Right? If it said the summation as r goes from whatever number to infinity, then we couldn't pull out that r factor. So this so-called x to the r is just said to be a factor and not a recursive component of the summation. All right. So now you notice in the previous sections we could change the summation starting point because you look at the terms there. You plug in n to be 0. Then that summation at that particular value of 0 gave you 0. But here, it doesn't work like that. If you plug in n to equal to 0, we get the 3 c naught times r minus 1 times x to the negative 1. So that guy didn't go out, right? So we have to leave that as it is. Leave n goes from 0 to infinity. Can't mess with that because that guy is fixed. So what we what we want to do is to, in some kind of way, we have to figure out what r is. We have to figure out what r is. Well, how do we do that? Well, we go back to the previous method, the previous steps before, and back then we said, you see where you have, this is n minus 1, x raised to the n minus 1. This is x raised to the n minus 1. This is x raised to the nth power. And this is x raised to the nth power. So I want to be able to have this guy written as x to the k, if you will, somehow x to the k, and somehow x to the k, somehow x to the k. And so once I have that, we're going to factor out that x to the k. We're not going to factor out like we did the x to the r. We took the x to the r out completely of the summation because r does not tend to the terms of n goes from 0 to infinity. But we factor out the x to the k, if we can start the summation going from k to whatever term up to infinity, then we can say the summation, we'll factor out, or factor over, I guess is a better phrase, this x to the k, still leave it in the summation, but just try to make it less cumbersome for us because, granted, this is a lot of stuff, right? And so, and just one little mistake, it just throws off everything. So we don't want that. So, and if you go back and look at those steps here, we factor out the x to the r, replace n with some k factors. So that's what we're going to do right now. Okay. So for this guy, let's put this in blue. We're going to say let k equal to n minus 1. And so k plus 1 is equal to n. Same thing over here. Let k equal to n minus 1. K plus 1 is equal to n. And for this one, let k equal to n. And we'll just say for both of these guys. Okay. So we just write that now. So here x to the r, this is times 3 times summation. Here we're replacing this guy with k. So if n starts at 0, so this is k is equal to 0 minus 1, so k starts at negative 1 to infinity. This is c sub k plus 1. The n is replaced by k plus 1, so this is k plus r plus 1. And then this n is replaced by k plus 1, so it's k plus 1 plus r minus 1. That's just k plus r times x to the k. Okay. Move over. This is plus 2 times the summation. K goes from, well, if n starts at 0, then k starts at negative 1 to infinity. C sub k plus 1. And then this n is replaced with k plus 1 plus r. So this is k plus r plus 1 times x to the k. Minus, here for this one, for these next two, n is just replaced with k directly. So summation as k goes from 0 to infinity. C sub k times k plus r times x to the k. And then this is minus the summation as k goes from 0 to infinity of c sub k times x to the k. Close all that up. That's set to equal to 0. Does the problem stand out to you in terms of what you would have to do next? Why can't you do that right now? Exactly. Look at the first summation. K is starting at negative 1. The second summation, K is starting at negative 1. The third and fourth summation, K is starting at 0. So I cannot factor out that term right? Until I'm starting at the same values, right? Remember, k is the factor for the summation. This x to the r was not. So I could take out that x to the r without any loss of generality. Here, if I'm going to factor over, if you will, x to the k, this x to the k here associated with the x to the k there will be different because they're starting at different values. This guy's starting at k equal -1. This guy's starting at k equal to 0. So the way we overcome that is that we're going to evaluate the first two summations since they're starting at x equal -1 or k equal -1. We're going to evaluate those guys at k equal -1. So then the count next would be k to equal to 0 to infinity, okay? And so here, step 2, and step 3. Yeah, that's fine. Step 2 was we got introduced the k factor, so that should be a 2 here. Then step 3, evaluate the summation summations to have all summations starting at the same point. So to do that, we just evaluate this first summation and the second summation because they start at x equal negative. They start at k equal -1. So here we have that x to the r out in the front. Then so I'm going to evaluate the first one. This is 3 times. Here this would be c sub 0 if you plug in k equal -1. And then this is times, if k is -1, so this is r minus 1 plus 1, so that's just r. And then if you plug in k equal -1 here, this is r minus 1 times x to the -1. You see the same thing for the second one. This is plus 2 times c naught. If here k is -1, this is -1 plus r plus 1, that's just r times x to the -1. Okay. Now we can start the count at what we want. They all will start at k equal to 0 now. So this is the summation. Put a 3 there. K is 0 to infinity. Times c sub k plus 1 times k plus r plus 1 times x to the k. The next term plus 2 times the summation as k goes from 0 to infinity. C sub k plus 1 times k plus r plus 1 times x to the k minus the summation as k goes from 0 to infinity. C sub k times k plus r times x to the k minus k goes from 0 to infinity. C sub k times x to the k. That's all equal to 0. Okay. Step number 4. All right. I want you to look at it so that as I go through this process, the next thing that we do I want you to see where it comes from so that it'll be natural to you as it is for me. Right? This whole summations, all these summations are set to equal to 0. Right? All this stuff plus whatever equal to 0. Right? Which means that everything here must add up in some kind of way to 0. So remember the stuff that we took out? That 3 C naught times R minus 1 times x to the negative 1 plus 2 C naught, times R times x to the negative 1. This guy has to be equal to 0 too. Right? When you set that equal to 0, that's going to help you solve for those values for R. So let's do that. And once we do that, I solve for the values of R, I don't have to keep writing that first term anymore. I just deal with the summations hereafter. Right? So basically, we're saying the first part plus this guy has to equal to 0. So let's look at this in the confines of 0. So here, find the values of R. We do that by setting these terms here. By setting this guy right here equal to 0. You got to be careful because you got that x to the r sitting out there too. You need him too. Set that guy equal to 0. Set that guy equal to 0, divide through by x to the r, so that implies that we have here 3 C naught times r minus 1 times x to the negative 1 plus 2 C naught times r times x to the negative 1 equal to 0. Now this implies you can factor out C naught, you can factor out x to the negative 1 as well. C naught times x to the negative 1. So we have left 3 times r minus 1 plus 2r is equal to 0. Well, the goal is that we're looking for r, but I have C naught times something equal to 0, so we divide both sides by C naught, divide or multiply both sides by x, and that implies that we have here this 3r times r minus 1 plus 2r is equal to 0. So there we just solve for r. This gives us 3r squared minus 3r plus 2r, that's equal to 3r squared minus r equal to 0. Factor out of r, this is 3r minus 1. So this implies that r is equal to 0 and r is equal to 1/3. Those are our indicial roots. So, step number 5, we're now able to write the summations as 1, and we'll factor over that x to the k. So outside we have that x to the r times the summation as k goes from 0 to infinity. I'm going to go ahead and just put that x to the k here, and then this is times everything that we have left. That's why we use parentheses, since I got a bracket right there already. So this is 3. Got to go back, look at it. So here's all that we're writing. We're going to write these terms right here. All right. Let's see if I can grab this. Doesn't get all of it. We'll take what we can get. So that was raised to the kth power. You remember that? Now, I guess that's one advantage over the chalkboard, I guess. Yeah, but still, I prefer the chalkboard. So here, so the part that we're writing now is going to be this stuff here, and all of that. I'm going to write it as one summation. So I factored out I'm sure this was x to the k as well. So I factored over the x to the k. So I have left 3 times the c sub k plus 1 times k plus r plus 1. Then I come over to this guy. This is plus 2 c sub k plus 1 times k plus r plus 1 minus c sub k times k plus r minus c sub k. Close the parentheses, close the bracket, equal to 0. Okay. Good. So let's see. I think that was step number, the last thing I wrote was step 4. Is that right? Step 4. So now step 5. So step 5, what I want to do now is to be able to get a formula for the c sub k. Right? Here, this would be c sub k plus 1, that biggest term there. Right. So to do that, if you look at this entire equation, set to equal to 0, so if you divide through by x to the r, only focus on, this is a summation of what's happening inside. That's what's determining how we're able to get 0. Yes, sir. In the original one? I guess it didn't come over. Yeah, it didn't. It didn't transfer over in my copy, and I don't think you're exactly right. Thank you. That's right. It was n plus r, right? Or here, it came down to be k plus r plus 1, then a k plus r. Okay. Yeah, let's make sure I put that back over there. So this guy should be a k plus r there. K plus r times x to the k. And then here, gotta put that guy in there as well. This is k plus r plus 1 times k plus r. And that's plus sign there. Very good. Thank you, Austin. Appreciate it. So what we have is 3 times c sub k plus 1 times this k plus r plus 1 times k plus r plus 2 times c sub k plus 1 times k plus r plus 1 minus c sub k times k plus r minus c sub k is equal to 0. Alrighty. So now for the first two terms, I can factor out c plus k plus 1 and also factor out k plus r plus 1. Then from the last two terms, you can factor out a negative c sub k, or just get that guy on the other side anyway. So this right here is c sub k plus 1 times k plus r plus 1 times brackets 3 times k plus r plus 2, and that's equal to c sub k times k plus r plus 1. See that? For the right side. So I'm getting this term over there. I'm getting that term over there, right? Then I just factored once I got over there. They both had it becomes plus signs on the right side, and they have a c sub k in there. So factor that out. This is k plus r, then this is plus 1, right, on the right side. So now we're going to divide both sides by the k plus r plus 1 and divide both sides by this term here in the bracket. So then I have left c sub k plus 1. That's equal to c sub k all over 3k plus 3r plus 2. The k plus r plus 1 would cancel out on both sides, right? So that's our formula. So now we get right back to how the problems looked in the previous section, but now we have an R factor. Right? So here's how we get to solutions. So first you have to, this is step number 6. Solve the coefficient formula. This is the formula here. In terms of R. So here we got two values for R. One value was that R is equal to 0. The other value was that R is equal to, I think, 1/3. So you take R equals 0, you solve for this formula for the coefficient. So C sub k all over 3k plus 2. All right, so if k is 0, we get c sub 1, excuse me. So we get c sub 1 is equal to c naught, k is 0, it's just 2. C sub 2, we get c1 over here, k is 1, so it's 3 plus 2 is 5. C sub 3, we get c sub 2, 2 times 3 is 6, plus 2 is 7. So the bottom term just increased by 2, basically. C sub 4, C sub 3 is C sub 2, all over 2, 6, 7, 8. Yep, thank you. Yeah, I was looking at the next one, like that's not working out right. Yeah, so they're not increasing by 2, I'm sorry. This is 3 times 3 is 9, and 2, that's 11. All right, very good. I guess that'll be fine right there. So let's see. This guy is equal to, it's based off of C sub 1. So this is C naught all over 2 times 5. This is C naught all over 8 times 2 times 5. And this is C naught over 11 times 8 times 5 times 2. Okay. And so here, this value for y sub 1, if you will, is get C naught plus C sub 1 times x plus C sub 2 times x squared plus C sub 3 times x to the third, and so on. So this is C naught, and then C sub 1 was C naught over 2 times x plus C naught over 2 times 5 times x squared plus, oh man, where does the time go? This is C naught over 8 times 5 times 2 times x to the third plus, okay, you kind of get that. Part B, take R to be 1/3. So we go back up to that formula there, we plug in, not that one, this one, R to be 1/3. So we get C sub k plus 1 is equal to C sub k over 3 times k plus 3 times r, that's 1/3. I think it's a plus 2, yes. So this is C sub k all over 3k plus 3. So we get C sub 1, which is C naught all over 3. C sub 2 is C sub 1 over 3 plus 3, we get 6. C sub 3 is C sub 2 over 6 plus 3, we get 9. And C sub 4 is C sub 3 over 12. See, 3 times 3 is 9 plus 3, yeah. And so this guy is C naught over 6 times 3. This is C naught over 9 times 6 times 3. And this is C naught over 12 times 9 times 6 times 3. So now the solution for this guy, y sub 2, is x to the 1/3. That's that The other one was x to the 0, so you didn't really see it. That's that R factor times C naught plus, now C sub 1 is C naught over 3 times x. C sub 2 is C naught over 6 times 3 times x squared. Just put one more there. Plus C naught 0, 1, 2, 3. This is 3. 9, 6, 3 times x to the third plus, and so on. So you write the final answer. Guess I can get it here. That y is equal to, that first term up there was, you don't see the x to the naught because x to the 0 is just 1. So if you take out the C naughts there, this is just C naught times parentheses 1. Don't see it. Plus x over 2 plus x squared over 10, and I'll stop it at that one. Plus, and so on. Close that up. Plus x to the 1/3 times C sub 1. We got C naughts there, but not to be confused with these C naughts, we just call it C sub 1 times here, this is 1 plus, looking at this guy, x over 3 plus x squared over 6 times 3, and you get the picture. Okay. Whew. That's a lot for one problem. Okay.